Assalamu alaikum. It's our ninth lecture of Advanced Electromagnetic Field and Waves, and in this lecture, we will start chapter number 7, problem 7.2. Okay, so in problem 7.2, what it says, a plane wave is incident on a layered interface. Okay, as shown, there is a plane wave, okay, which is coming. The indicates of reflection of the three non-permeable medium, okay, are n1, n2 or n3. There are three non-permeable mediums. This is n1, this is n2, and this is n3 similarly. And you are watching that your plane wave is coming. This is the direction of electric field of the plane wave, and this is the direction of magnetic field, and definitely this direction is the direction of wave vector k. As you know that wave vector, magnetic field and electric field are always perpendicular to each other. So this plane wave is incident on a layered surface where there are three non-permeable mediums n1, n2 and n3, and the thickness of the intermediate layer is d. As you can see, this is the thickness between the layers. For n1 equals to 1, n2 equals to 2, n3 equals to 3, and n1 equals to 3, n2 equals to 2, and n1 equals to 1, and similarly n1 equals to 2, n2 equals to 4, n3 equals to 1. So what you have to find, calculate the transmission and reflection coefficient. Okay, so you have to find the transition and reflection coefficient, okay, ratio of transmitted and reflected polynomial flux to the incident flux, and sketch this behavior as a function of frequency. Okay, as I told you, n1 equals to 1, n2 equals to 2, n3 equals to 3, and so on. Okay, and the b part is basically the medium n1 is a part of an optical system. Example lens. Let's suppose your n1 part, n1 region medium, is basically a part of an optical system, and medium n3 is an air. So for the case of air, so n3 equals to 1. So it is desired to put an optical coating medium n2, okay, on the surface, so that there is no reflected wave for a frequency w0, what's thickness d, and index of reflection n2 are necessary. So this is our problem number 2. We are going to solve this problem in this lecture number 9th of Advanced Electromagnetic Field and Waves. So let's start. So first of all, we have to organize our coordinates. Let's suppose these are our coordinates, okay, and this is z direction, this is x direction, and this is y direction. Okay, and in our case, this direction is given. In x-axis is basically the direction of electric field, and in z-axis is basically the direction of wave propagation k, while your y direction is basically the direction of magnetic field b. So let's start our problem. So as you know that there are three regions, let me draw in our problem. Okay. This region is, you can say, n1, this region is n2, and this region is n3, and here your wave is coming. This is the direction of k, and upside is the direction of e. Similarly, this direction is for b. Okay, so what you have to do in this, first of all, you have to write the electric field and magnetic field wave equations for different mediums, for different regions. Like first of all, you have to find electric and magnetic field in region 1, then in region 2, then in region 3. Okay, so how you can find this? This is simple. You can draw this because let me draw this as this diagram. Okay, like this is region 1, this is region 2, this is region 3. So your wave is going into region 1, then it again goes into region 2, then it transmitted into region 3. Definitely when your wave is going into region 1, crossing this boundary, it is transmitted somehow, and some of the wave reflected back. Okay, similarly, when your wave is going into region 2 and have to move forward into region 3, what would happen that your wave is transmitted somehow in region 3 and some of the wave is reflected back. And when your wave is in region 3 and now there is no reflection back, now you can see there is no boundary here. If there is no boundary, so there is only transmission, there is no reflection back from region 3. So now what's your problem is basically you have to route the electric and magnetic field in all three regions, region 1, region 2 and region 3. So let's solve this first for region 1. Okay, let's first solve it for region 1. First of all, let us make a wave equation for the case of electric field. So in this scenario, you know that the electric field is going inward and your electric field is upward. The wave is propagating in this direction, means z direction, and while your electric field direction is in the x direction. So what's basically the incident electric field is basically, you can write ei, which is equals to, because you know that electric field in the x direction, okay, whereas the magnitude e naught I, okay, and similarly e power iota k1. Why k1? Because we are in region 1, and what is the direction of wave propagation, or the wave vector k is in the z direction, so it becomes iota k1z minus iota omega t. Okay, this is going into incident, so we can say that vi plus. Okay, coming electric wave. Now also it's reflect back, because when your wave is going into this medium, it is going incident and some of the wave is reflected back. So let us write for the reflection part, and our reflection part is denoted by er, and basically it's equals to this e naught r, which is the magnitude. Okay, similarly e power iota. But you see, when your wave is coming back, what would happen? You can see the direction of this wave vector changes, but the direction of you can see that the direction of uh, magnetic field also changes. Okay, in this scenario, when this scenario your wave is going into, so the direction of k is in the z direction, but when it strikes and comes back, now the direction of wave vector is in the opposite direction. Is it in the z direction, but is it in the negative z direction? So you can write the direction of uh, wave is minus iota. Okay, minus iota k1z, because you are again in region 1, minus iota omega t. Okay, the direction of electric field not changes, because you can see the direction of electric field is in x-axis. Either it is going and it is reflecting back. The direction of electric field not changes. Only what changes, the direction of the wave propagation k changes. Okay, so this is for incident and this is for reflection back. So you can write it as minus for reflection back. Okay, now what you have to do, you have to write magnetic field wave equations also. So let's write magnetic field wave equations. How we can write? We can write simply by, let first initial incident magnetic field bi, which means incident, and plus means going into. Okay, what's the direction of magnetic field when your wave is going into? Is it in the y direction? How you can find? You can easily find by right hand rule. So this is your right hand rule. You have to align your fingers in the direction of electric field. Your electric field upper, you know, electric field, and you have to align your thumb in the direction of wave propagation. Okay, the direction of wave propagation. So wave propagation is here. Now what you have to do, you have to curl your fingers. This is x. You have to curl your finger into the y-axis. Y-axis is this. So you can see. So this is out of the page. Okay, out of the board. This, my curling of finger is basically out of the page. That's why for the case of out of the page, we are going to use plus y direction for incident. Okay, means y direction, as you see here. y direction, and what's its magnitude amplitude is basically b naught I divided by c, because you know that basically you know that b naught is equals to e naught divided by c. This is our formula, but here in the case this is c replaces by v1, velocity in the first medium. Okay, and similarly the other equation is same, because e power, okay, e power again you can see in incident your k direction is in this, means positive z direction, so it becomes k iota k1 z minus iota omega t. So this is your equation for the magnetic field going into the first medium. Okay, now magnetic field going into first medium also it will reflect back, so let's write for reflection back. So it becomes b reflected minus, why minus, because let's suppose your b field is reflecting back. Okay, that's why I'm writing minus. But now because your in this is for the case of reflecting back, this is going for the into, and this is for the going outgoing. When your wave is going out, now the direction of b field changes. Okay, how we can check? You can see again I have to align my fingers. Now what I have to do, I have to uh, put my thumb in the direction of k. Where is k? K is not here, k is here. So this is correct. So this is my fingers in the direction of electric field, and this is my thumb in the direction of k. What I have to do, I have to curl my fingers to find the direction of b. So curling my fingers, so it is going into the page or into the board. So for into, cross means into the page. Okay, so for the case of into, okay, your always direction is negative, so we are now using negative y direction for the case of when your magnetic field is reflecting back into the first medium. Again b naught r divided by, again you are in first medium, so this again again for the case wave vector direction also changes. Incident is wave direction here, but after reflecting your wave direction is here, it changes, so it becomes minus iota k1 z minus iota omega t. So these are the equations you can write. Okay, let's finalize these equations into a combination form, how you can combine these equations. So let combined form of these equations are, you can write E1. Okay, electric field combined equation is, because direction is x, as you know here x. Okay, take bracket E naught. Okay, again plus, okay, for coming e power I'm writing this plus this. Okay, this plus this is for the total electric field equation, iota k1 z minus iota omega t. Okay, plus e naught minus, okay, for the case of reflection I'm writing minus, for the case of incident I wrote plus e naught e power iota minus iota k1 z minus iota omega t. So this is the final combined equation of electric field. Okay, make equation as A. Let's write the general equation, combined equation for the magnetic field also. In first region, that's why one magnetic field, as you know, is in the y direction, so I'm taking y as common. So what is left basically? Basically left is there is the left case is E naught divided by V1 for the case of plus, means incident, e power iota k1 z minus iota omega t. Okay, similarly this is minus, so we are minus e naught divided by v1 e power minus iota k1 z minus iota omega t. So this is our general equation for combining. There is no b here, here is the e naught. Okay, because you know that here is initially B naught, but I replace B naught equals to E naught by C, means E naught by in one region is V1. Okay, so that's why this equation. So these are your final equations of electric and magnetic field in region 1. Now we have to do the same procedure for region 2, and then we are going to do same procedure for region 3. Okay, so let's start. Now your wave is in region 2. Again in region 2, some of the wave going into region 3 means okay, and some of the wave again reflect back into the region 2, because there is a boundary. Okay, some of wave is transmitted and some of the wave is reflected back. So we have to write the same electric and B fields equation for this for region 2. Okay, now we are solving for region 2. Okay, for region 2 we should say that again E. Okay, now your E plus basically, okay, you should write EI for the case of incident. Now for the again, now your electric field is in region 2. Okay, now it is going into region 3. So again the direction of electric field is in the y-x direction not changes of the electric field x, and amplitude E naught I for the case of going into incident, so plus. Okay, E power, again this wave is going into, so again the direction of wave propagation k is in positive z direction, and B is in the positive y direction. Okay, so E power iota k2z, why k2? Now because you are in region 2. Okay, minus iota omega t. Similarly, let's write for the reflected wave of this ER, which is equals to reflecting back from this is same scenario, because you see that your electric field is in same direction, so x becomes x direction. E naught R E power, only the direction of wave propagation change, E power minus iota k2 z minus iota omega t. Similarly, you have to write for B field, Bi coming. Okay, it's same as in region 1. Okay, how you can write, you can write, because B is going into, what's the direction of this in this scenario, going into means is in the positive y direction, so it becomes positive y direction. Okay, E naught divided by V2. Why V2? Because now you are into the second medium. Okay, and E power wave propagation direction is going into same z direction, so it becomes plus iota k 2z minus iota omega t, while magnetic field reflected back equation is this. When it's coming back, as you see now it's into the page, from this into the page, so for the case of into it becomes negative y direction, and E2 divided by V2, and E power k direction also inverses for the case of reflection bias, minus iota k2z minus iota omega t. Now what you have to do, you just have to combine these combined form of these equations you have to write as we write for this case. Okay, so let's combine these equations, so it becomes okay. Now for the case of second, it again what it becomes 1, so you can write, sorry, 2. Now you have to add this both, x is common, direction is common, take x direction common. Now what it becomes, E naught plus E power iota k2z minus iota omega t. Okay, plus E naught minus, for the case of reflection, okay, reflecting back I am taking minus, and E power minus iota k2z minus iota omega t. Okay, similarly for the case of B field, combined equation is take y as common, so it becomes E naught by V2 for the case of plus E power iota k2z minus iota omega t. Similarly minus sign, so minus E naught minus divided by V2 E power minus iota k2 z minus iota omega t. So these are the generalized equations for region 1 and for region 2. Okay, now the final part is to write the equation when your wave into the region 3. But you can observe that in region 3 there is no other boundary, so there is no reflection back, only transmission. So your wave is transmitted, your wave is not reflected back. So how you can write your equation for the case of region 3? First of all, let us write electric field equation. You can suppose by ET means transmitted, it becomes, again the direction is x, so it becomes x. Now E naught t for the case of transmitted, e power iota k3z, okay, because now in third medium direction of kz, that's why z minus iota omega t. There is no reflection back, so there this should be 0, so we are not taking this. Okay, no reflection back. So for whereas the magnetic field concerned, again the magnetic field is in y direction, it becomes, okay, e naught divided by v3, okay, and e power iota k3z minus iota omega t, because your magnetic field is positive. Okay, your wave vector is also positive and we field also positive and going into no reflection back, so no reflecting medium. Now what is your work is to find, as we see the in problem, we have to find the transmission and reflection coefficient. Okay, how you can find transmission and coefficient? By using boundary conditions. Okay, how we can use boundary conditions? We know that we have four boundary conditions, that we know that the tangential components of electric field E and magnetic field H are equal. Okay, while your normal components of electric field D and magnetic field B are equal. Okay, so in this, which boundary conditions we are going to use? We are going to use two boundary conditions. One is basically the tangential component of electric field is equals E1t equals to E2t, and the second boundary condition we are going to use, because we have B, and so we know that they are not equal. Okay, B1t are not equals to B2t, because you know that the tangential components of B fields are not equal, only normal components are equal. Okay, our work is to find the transition coefficient and reflection coefficient, so we have to apply boundary conditions here. And boundary conditions, we are assuming that at z equals to 0 here. Okay, at boundary, so at boundary z equals to 0, so what we have to do, we have to apply boundary conditions on these equations by approaching z equals to 0. So what's our, as we know that whenever you z equals to 0, okay, so 0 multiplied by this e power 0, e power 0 becomes 1. As you know that e power 0 is equals to 1. Okay, as e power equals to 0, so you will only left with what? Let us first do this. First bound by first boundary condition, e1t equals to e2t, these two equations. So when your z equals to 0, so what it becomes, only you will left with what? You will left with, okay, e plus, and you can say that e plus for the case of 1, and plus e minus 1, which is equals to, for the case of second, e plus 2, which is plus e minus 2. Okay, because exponential term become equals to 1 when you are applying the boundary conditions. So this is your main equation for the case of electric field, because you know that the tangential components are equal. Okay, while when we are using the second boundary condition, whereas you know that your b1t is not equals to b2t, t. But how you can write? Again, you have to use this boundary condition at z equals to 0. When z equals to 0, these exponential terms for the case of b become 1, and you will left with what? You will left with only e naught plus 1 divided by v1 minus e naught minus 1 divided by v1 equals to, okay, e naught plus 2 divided by v2 minus e naught minus 2 divided by v2. This is not minus 2 minus 2. This is plus 1 for the case of incident and minus 1 for the reflection back. Again plus 1 for reflection and plus minus for the, and this one is for first medium and this 2 is for the second medium. Okay, and you can not equal because you know that these are not equal. So this is how you can find reflection and translation coefficient. Now simply you can find by, you know that the formula to find the transmission coefficient is, as you know that to transmission coefficient formula is basically e naught t divided by e naught I. Means you have to divide your transmitted part divided by the incident part to get the transmission coefficient. Okay, transmission coefficient. Whereas how you will find the reflection coefficient is, you can find it by, you have to divide your reflected part divided by initial part to get the reflected coefficient, reflection coefficient. So this is how you can solve this problem 7.2 of chapter number 7 of advanced electromagnetic field and waves. So that's all for today. For this lecture we will upload more lectures, so like and subscribe, share this video. Thanks for watching. Stay tuned with us. Allah Hafiz.